Hi students, Professor Nugent here. We are talking about the probit model in the context of a linear. We're talking about the probit model in the context of a binary dependent variable, and we have emphasized that the probit model is a little bit better at predicting the probability that our binary dependent variable equals 1, especially when we're thinking about low probability events or high probability events. That is when the probit model is especially better at predicting probabilities than the linear probability model. We're looking at the Home Mortgage Disclosure Act data, and we're going to run a probit regression. To run the probit regression, in data, we run the following code. We run probit y x comma robust, and our y variable is the dependent binary variable deny. Deny equals 1 if the mortgage is denied, 0 otherwise. Our x variable is the payment to income ratio, which is a variable that has been measured on a continuous spectrum. We have some iterations, and you see their log likelihoods because our probit model is being estimated using maximum likelihood estimation, and we're going to talk a little bit more about this later. I want to focus on the coefficients and the interpretation of this model in this video. So let's look at how we can first write down our model. We are predicting the probability that deny equals 1 given the payment to income ratio, and that's equal to the cumulative probability, that's the phi, that's the function of z, where this is our predicted value for z here. This is the beta naught plus beta 1 times x, and we plug in our constant is negative 2.19 with a standard error of 0.16. That's the standard error for our constant, and the coefficient on the payment to income ratio is 2.967908. So we plug in the value of the beta 1, 2.97 times the payment to income ratio with a standard error of 0.47. So this is our estimated sample regression, where the predicted value of z is negative 2.19 plus 2.97 times payment to income ratio. And then the phi represents that this is the probability that z is less than the value of this at the payment to income ratio equal to some value, say 0.3. Let's continue with this example. Does it make sense that we have a positive coefficient so that the probability of deny is higher with a higher payment to income ratio? In other words, it does make sense because our z will go up as the payment to income ratio goes up, so the predicted probability goes up given that we have a positive coefficient. And that's what you would expect because you're more likely to be denied if you have to contribute a higher proportion of your income to your mortgage payment. The standard errors have the usual interpretation, so you can construct test statistics for these, oh my goodness, you can carry out test statistics for these coefficients. Now let's think about the predicted probabilities. First, let's just write down the test statistic. The t-stat, this may be 2.97 minus 0 over 0.47. That's your test statistic. And you can compare that to your 1.96 critical value at the 5% level of significance. Now let's look at the predicted probabilities. What is the probability that an application is denied given a payment to income ratio of 0.3? So we plug in, using our sample regression, negative 2.19 plus 2.97 times 0.3. So the value of z is negative 0.13. The probability is 0.097. So the probability that an application is denied given a payment to income ratio of 0.3 is 0.097. Now recall that what we're doing is that we're calculating the value of this z score, which is negative 1.3, and 0.97 is the amount of probability, the amount of cumulative probability up to 1.3. Okay, this is the probability that an application is denied given a payment to income ratio of 0.3. What about a change in the payment to income ratio of 0.3 to 0.4? Well, let's calculate the probability that an application is denied given the payment to income ratio of 0.4. We find that that is 0.159. So the probability of denial rises from 0.097 to 0.159. Okay, 0.097 to 0.159. Now we can think about multiple regressors as well. We can have as many regressors on the right hand side as we like. For example, we could have 2. In this regression with the big rainbow star, we have that the probability that y equals 1 given x1 and x2, and then that's our predicted value for z, and phi is the cumulative normal distribution function. Z is equal to beta naught plus beta 1 times x plus beta 2 times x2. This is our z value, or z index of the probit model. Beta 1 is the effect on the z-score of a unit change in x1, holding constant to x2 when a causal interpretation is justified. So we have added an additional regressor, but all of the principal foundations of the probit model that we have discussed, this does not change. So let's look at our example where we have also added an additional variable, and in this case the additional variable is a dummy variable. The dummy variable is black equals 1 if the applicant is black. And so we have run the following code: probit deny p underscore irat black comma robust. All right, and that's probit your y variable x1 x2 comma robust, and the coefficient on the black variable is 0.708, and this tells us that the probability of being denied given that the applicant is black is higher than the probability of being denied given that the applicant is white, all else equal. All else equal. So we can calculate those predicted probabilities, the predicted probability for a black applicant and a white applicant, using the following code with the regression results that we have just run. So we can generate a scalar. That's what this code SCA means. SCA Z1, scalar Z1 is equal to underscore beta bracket underscore constant plus underscore beta PIRAT times 0.3 plus underscore B black times 0. So we're generating this scalar Z1 using the estimates, the coefficient estimates. The underscore beta is the coefficient, the underscore constant. This is drawing from the data. And what we're doing here is we're pulling in the value that the payment to income ratio is 0.3. Okay? So we want the coefficient, the beta of the constant, we want the intercept. So as to say, we want the coefficient on payment to income ratio. We're multiplying it times a payment to income ratio of 0.3. And then we want the scalar for the white applicant. And we're going to display the following text: predicted probability for payment to income ratio of 0.3, comma, white applicant, and that's equal to, and we want the normal probability of that scalar Z1, and the normal probability is 0.075466603. Alright, so again, this code is our estimated intercept for this regression. This code is the coefficient on our payment to income ratio. SCA creates the new scalar, which is the result of the calculation, and display prints the indicated information to the screen. Now let's finish out this example. The probability of deny given payment to income ratio and black is this regression, which comes from that regression table. We can ask, is the coefficient on black statistically significant? And we would solve that using our standard test statistic. You would do a t-stat, which is 0.71 minus 0 all over 0.08. And that looks statistically significant to me. The estimated effect of race for payment to income ratio is 0.3. Let's look at the probability deny equals 1 for black and white applicants. We just solved the probability that an applicant is denied given payment to income ratio equal to 0.3 and that they are white, it's 0.075. The probability that an applicant is denied given payment to income ratio of 0.3 and black is 0.233. So the difference in the rejection probabilities is 0.158 or 15.8 percentage points, which is quite large. Right, so two people with the same payment to income ratio, one is black, one is white, the black applicant has a 15.8 percentage point higher chance of being denied. There is still room for omitted variable bias, so we want to control for more demographics, but this is the idea of what we're doing here. In the next video, we're going to discuss another model, which is called the logit model, but is similar to the idea behind the probit model.